All right, so let's go ahead and get started on our actual course material for Math 107. So I know it's conventional for us to start in the first chapter of the book, but we've found that starting in chapter 2, it's a slightly easier, sort of jumping off point for students. So we're going to be talking about a couple of different topics in chapter 2, but we're going to start by talking about a branch of mathematics that's known as set theory. So, as you can read on the PowerPoint slide, set theory is relatively young in mathematical terms. Mathematicians didn't really start studying sets as mathematical objects until the 1800s. So that's compared to, say, calculus, which has its origins in the 1600s, or something like geometry, which goes back to, BCE type time frames. So mathematicians initially began looking at sets, sort of trying to examine the structure of what we would normally call the real number line. So I'm sure you've had to draw a number line at some point in the past. And as it turned out, mathematicians found more and more, ways that we could deal with collections of objects that weren't just sets of numbers. So that's what we're going to be talking about. All right. So one of the obvious questions that might end up coming up is, what do we mean when we talk about a set? Now, set is one of those sort of weird words in the English language. I think if you go look in like the OED or Webster's, set has like 100 different definitions. For our purposes, set really just means a collection of objects. That's probably where your mind went first, but just in case, we're not talking about like what Jello does in the fridge or anything. So a set is a collection of objects. They may be numbers. We'll see, some examples where we do have numbers, others where we don't. Uh, the key thing to point out is that we can tell clearly, beyond a shadow of a doubt, whether or not something is in fact in the set or is not. So those things that are in fact in the set we refer to as elements of the set. So if you hear me say elements, or reference, X is an element of some set A, we'll often use like capital letters to represent sets, and then something else to represent the individual elements inside them. But yeah, so that's what we're going to be talking about. So let's take a look at a few examples real quick of collections of objects and see if they meet this criterion for being a set. So the collection of United States presidents. Well, if I give you the name of a person, you can, immediately like go check on Wikipedia or whatever and determine whether or not that person has in fact been president of the United States. So like Barack Obama is a yes, he is in there. Philip Carroll, your instructor, has never been US president. Thank heaven for that. So yeah, I would not be, an element in this, collection. So we can clearly tell this is in fact a set. On the other hand, if we were trying to talk about the 5 best movies of all time, well, that one is a little bit trickier, right? Because it's like, what do we mean by best? Like, if I were to ask each individual person in our class what their favorite movie is, I'm going to get a different answer from just about everybody. So that's a common kind of issue there. Is this what you would call subjective? Like maybe if we defined best in terms of like movies that had won the most Oscars, and then we'd have to qualify what we mean by most, or the 5, as you're saying, or the 5 highest grossing movies if we wanted to look at how they, how much money they'd made in the box office or in video sales or whatever. In any case, so number 2 here isn't really a set. There's no clear distinction for whether or not a given movie is in here or not. The subjectivity built into best is kind of a problem for us. Um, so lastly, if we took a look at the collection of all even numbers between 0 and 100, again, I think hopefully this makes sense. It feels a little more mathematical in nature, but yeah, it feels like something. If I give you a number, well, you can tell whether or not it's between 0 and 100. You can tell whether or not it's even. So yes, we can clearly specify exactly which numbers do in fact live in this collection. So this one is a set. Okay. So we've talked about what a set is. So if we try to talk about describing a set, there are a few different ways we can do it. So on the one hand, we've got a verbal description, which we just did, right? The collection of people who have been United States president, the collection of even numbers, between 0 and 100, something like that. The other two are a bit more involved. So on the one hand, you have what you might call the roster method of describing a set, which is just sort of a straight up list of everything that is in fact an element in the set. So if we were to take that collection of even numbers from earlier, we could list it like so. Like I said, we use capital letters, and we generally enclose a roster inside these curly braces like you see here. So the even numbers between 0 and 100, 2, 4, 6, 8, who do we appreciate, the deal. Um, Generally speaking, if a set is really long, we'll often use those sort of three dots and ellipsis in there to indicate that there's a pattern. You should be able to pick up on the pattern and see how it continues. So you'll see we started with 246. Everything following that same pattern up until we get to the 96, 98 at the end would be an element of the set. So that's the roster method. The last one is a bit more technical. It's something where we use what we call set builder notation, which is kind of a mathematical shorthand. For a lot of non-mathematical sets, like presidents or something, the set builder notation will just end up looking like kind of a weird, awkward, restatement of a verbal description. But if you've got other math symbols to cut down what you're describing, it works out pretty well. So you take a look at rearranging the set of even numbers that I listed earlier. So the format here, if I were to read this thing out, I would say that E is the set of all X. So that X at the front is X. That vertical bar we'd normally read out mathematically as such that or satisfying or something along those lines. So the set of all X such that X is even, and then 0 is less than X, which is in turn less than 100. So, or you could say X is greater than 0 but less than 100. So that's set builder notation in action. As I said, if you were dealing with a nonverbal set, it can be a little bit more awkward, and it can feel weird if you've got like letters or something like that. Remember, X is just a placeholder in this instance. So, all right, so that's set descriptions. We've talked about what a set is. We've talked about how we can describe it. A couple of other things we kind of need to talk about in terms of setting the table before we really dig into what you might call set operations. We're going to need some notion of what we would call the cardinality of a set. So cardinality can get kind of technical. For our purposes, you can just think of a cardinality as basically a count of how many elements there are in the set in question. So yeah, that's pretty much what that is. You see the notation right there, that N of A that you might have noticed when you looked at the WebAssign tutorial. That is sort of math notation for the cardinality of whatever set is living inside those parentheses. So that's not a multiplication. It's what math folks would call a function. Anyway, one more thing I want to point out as far as cardinality is concerned before we move on here is that don't count elements that end up getting repeated when you calculate a set's cardinality. So, for instance, a set that was just the number 1 7 times over, it doesn't have a cardinality of 7. It actually would only have a cardinality of 1. The only element that's in there is, in fact, the number 1. As another example, so I like to end up, polling students about what their favorite movies are. So, from a few years ago, this is what I ended up getting in response, from a particular class of students. I had them email me what their favorite movies were. All right, so we had this, group of favorite movies, and this is what I ended up getting. This one was, I always kind of like looking at this because I find it amusing to look and see how many of the movies I actually recognize names for. This one was a bit, less, like I had to go pop open Wikipedia and keep looking up what was going on. I think, other than the perks of being a wallflower, I, knew them all. So I felt good about that. Made me feel less old. Anyway, so now if we were to make this a set, call it M of, class favorite movies, and we wanted to know what the cardinality of this set is, well, you can kind of like count the bullet points I've got sitting next to the movie titles, and you'll notice that's 23. So for the record, do keep that in mind that when we say, even though 2 different students told me that The Fast and the Furious was their favorite movie, that doesn't mean that there were actually 24 elements in the set. We don't count that repeated thing. It doesn't matter if, half the class had said that The Fast and the Furious was their favorite movie. We only count it the one time as far as cardinality is concerned. So do keep that in mind when you look at things. Repeated elements, don't count them again. All right. So, a couple more concepts we're going to need sort of going forward. Like I said, there's a fair bit of terminology that goes into this. I just, like to describe these things. So, every now and again, we'll have to deal with a set that actually has nothing in it. Mathematicians refer to that as the empty set, and the notation we use to describe it is this thing that looks kind of like a circle or a zero with like a slash through it. Um, it's kind of a corner case to cover our bases in some sense. But the big thing to keep in mind is that the empty set is not the same thing as the set that contains zero. I know zero is usually sort of our like representative for nothing, but in this instance, the set containing zero has one element, that element being the number zero. The empty set really does have nothing in it. So if you were like to write it out in roster form, you would just have those curly braces with nothing in them. So we don't normally write that. And for what it's worth, working in WebAssign, if I remember right, I think you're just supposed to type in like empty in all caps. So it's not even like you really need the symbol. But I did want to mention it in case you happen to be looking through the textbook and saw it pop up. All right, last thing I want to talk about in terms of like getting the terminology and the jargon and stuff in place is the notion of what we mean when we talk about a subset. One set being a subset of another. So it kind of means that the smaller set lives inside the bigger set. Everything in A is also inside B. So our notation looks like this. A was sort of a U that got turned over on its side, indicating the subset relationship. So here, everything in A is also in B. Our text will distinguish between proper subsets where they put sort of an or equal to symbol underneath the that subset symbol right there. For our purposes, that really doesn't matter. It's the kind of thing where I've been studying mathematics for a good couple of decades now, and the number of times I've needed to worry about that, or equal to distinction, I could count on one hand and still have fingers left over. So for our purposes, like I said, it's not something we'll have to write a ton, but just in case, that's the difference that ends up popping up there. So we've talked about sort of the basics here. This notion of subsets is going to be pretty important because generally speaking, what we're going to be doing in the future, we tend to think of our sets in question as living inside some bigger set. So that's where we'll pick up in our next video.